Hello, everyone, and welcome to Signal Systems and Signal Processing with Wolfram U. This lesson is on modeling discrete time systems as difference equations. In this lesson, we will look at three popular LSI systems, or linear and shift-invariant systems, and we model them as difference equations. These systems are moving average system, compound interest, and exponential growth and equalization. We will see with these examples how we can obtain the output of any of these systems using a simple recursive numerical calculation. An important class of LSI systems is characterized by a linear difference equation with constant coefficient in the form shown here. Here, y of n is the output and x of n is the input sequence. These equations can be solved analytically similar to the differential equations, and we can obtain an explicit solution for y of n, but also we can solve them numerically for any value y of n by recursion if we have the n preceding values of y of n and, of course, the input sequence. These systems are called recursive systems. There is another set of important class of systems called non-recursive systems, which are modeled by difference equations in the form shown here. These equations are independent of past outputs. Here, the output sequence y of n does not depend on the previous values of y. As you can see on the left-hand side of this equation, we only have y of n, no previous values of y. Y of n, that is the value of the output of the system at any time n, is simply a weighted average of a number of values of the input sequence x of n plus one of them here to be exact. Let's look at a moving average system as our first example of LSI systems. This is probably the most frequently encountered discrete time system in practice. A moving average system is used to smooth an input sequence by reducing the variations of the sample values of the input sequence. It does that by taking the average of those values as shown in this difference formula given here. As you can see, it is also a non-recursive system. The output value y of n depends only on the values of the input sequence x of n and not on the previous values of y itself. Y of n is simply the mean of n present and past values of the input. Here on the left-hand side, we have plotted the data from a row of the image that you see on the right-hand side. We do this so you can see the averaging or the smoothing effect on both the data values and the image itself. We also look at the effect for changing values of n. As we increase n, you can see how the image is getting smoother and for larger values of n, blurrier. When n is equal to 10, for example, here you can see how the output shown in orange is smoother than the input sequence shown in blue, and the image is also smoother. Another system is the system of compound interest. Compound interest is used in most transactions in banking and in finance sectors. And it is the process of adding interest to the principal sum or principal value of a loan or deposit. For example, in a saving account, the principal value at any time n, denoted by y of n, will be equal to the principal at time n minus 1 plus the accumulated interest, r here is the interest rate, and any deposit or deductions x of n that we may have at the current time n. We have a first-order difference equation that we can simplify and rewrite in the standard form shown here. Let's plot the output sequence, the principal y of n, using the Wolfram language to see the effect of compounding the interest on y of n. With an initial deposit of $1,000, let's say, and no further deposits or deductions, x of n is equal to 0 for n greater than 0. And let's have this plot for different values of the interest rate. Starting from 1,000, if the interest rate is 0, the output, or the principal, remains at 1,000 since there are no external deposits or deductions. Changing r to be this positive value, you can see the principal is growing exponentially. Now, note that if we were to model the increase or decrease of some population, model the growth of some bacteria, for example, or other similar examples, we would again get a first-order difference equation similar to what we obtained here. In the previous examples, the systems were modeled by first-order or second-order difference equations. These equations, and in general, an nth-order linear difference equation with constant coefficients, can be solved numerically by iteration, given that we have the input signal x of n and n initial conditions. Assuming we are interested in the values of y for n greater than or equal to 0, the initial conditions would be n previous values of y starting from y minus 1, y minus 2, and so forth up to y minus n. Rewriting the above equation, y of n will be equal to the expression shown here. Starting from n equal to 0, we have the value for y0, then y1, and the rest of the values of the output can be found in a similar way. Let's use this numerical method in an example. Given this first-order difference equation and initial condition, let's find the output sequence y of n for n equal to 0, 1, 2, and so forth, if the input sequence x of n is given as cosine of n pi or minus 1 to the power n. Using the Wolfram language, we can solve the recurrence equation to get a list of the output values for n equal to 0 through 3, let's say. We can generate more values and plot them to see how they change over time. Now, if we were to find these values by hand, we would start by rewriting the difference equation as shown here, so that we have only the term y of n on the left-hand side. And then recursively find the values of y of n, starting from y of 0, replacing y of minus 1 here by 0, we get 1 for y0. Repeating the same step, we get the value of y1 as indicated here, y2, and so forth. You can check and see that these results match the values found by the Wolfram language. In this lesson, we looked at some examples of LSI systems, linear and shift-invariant systems. Each of them had some practical application. We also presented the ordinary difference equations with which these systems were modeled, linear difference equations with constant coefficients. We went over the numerical methods of obtaining the output of these systems and LSI systems in general, assuming that we have the input sequence and the initial conditions. Given these values, to find the values of the output sequence, we recursively evaluated the difference equation.